Today we're going to be going back to the basics and I'm going to be showing you how to properly use a multimeter. And we'll be covering how to measure DC voltage, AC voltage, resistance and continuity, and also how to measure amps. Alright, let's start with DC voltage. Basically the main source of DC voltage in the different devices that we use these days are going to be batteries. Or in other words, anything that uses batteries runs on DC voltage. Hey, how's it going, dude?
好，OK，那我解一下。可以。但这边就，哈哈哈，帮我把这个往后推一点。你要坐那里也可以，然后往前推。OK。是加上传力流吧？我先看，我昨天看好像还没有。昨天的下午就在看到昨天过年我跟你说，很 Open circuit divided by 7 resistance, right? And for the open circuit voltage, because this is the voltage of the Vs, okay, of the R2 divided by the resistance, the equivalent resistance of R1 and R2, which is just a portion of this resistance, right? So the open circuit is R2, R1 plus R2 minus Vs, and what's the RTH? This is not wrong, okay? Assuming this is not wrong, so RTH is equal to R2, R1 plus R2 times Vs divided by I short circuit, okay? If you short these two terminals, and you want to find out the current, and this is nothing but Vs divided by R1, right? Because this is short together, so R2 is not working at all. Okay, so I short circuit is this is Vs divided by 1 only, not 1 only. So yes, okay, so you move the R1 to the numerator, so it becomes R1 plus R2, and the numerator is R1 R2. So this is the same as this, even though this is zero. Okay, so you need to realize, or you need to know the definition of the actual circuit, which is the ratio between the open circuit voltage to the resistance. Okay, so this is one thing I didn't mention last time. So next. Please get the textbook. And I think, yeah, pretty much we go through the impedance matching. So for the maximum power transmission, the load resistance is equal to the output impedance. Okay, the output impedance of the voltage source. IC is equal to R. In order to get the maximum power output, okay, we go through this. Okay. So this is the last part of chapter 2. It's about practical consideration. How to measure threshold. Because in our workshop we have 4 workshops. In the last workshop is for the robotics. We will go to the robotics okay, to do the workshop. For the first 3 workshops, we need to use the threshold. How to use the threshold? Some of you play this a little bit in high school. Some of you are not experienced this. A little bit about this, and I will show you some kind of guidance for you to avoid some messy connection with the threshold. I will show you like this. Okay. So it depends on how complexity of your circuit. Some threshold is very small, and some threshold is big. Okay. And I just want to show you how to make this. Okay. One voltage source and R1 is here, R2 and R3 are connected in parallel. Okay. Let's show you how to connect this in the threshold. Okay. First of all, there are 4 parallel lines. We call it power bus. Okay. Power bus. Okay. So then normally, because they are connected together, so it must plus and minus be a see here, normally we connect the power to this line and connect the ground to this line. Okay. But in between, there are a lot of colors, so colors, right? All the colors are connected together. Okay. And in this report is marked from 1 to 14. Okay. All the colors are connected together. So that means A, B, C, D are connected together. And C, F, G, H, C, F, C, G, H, C, G, H, I, J are connected together. Okay. Those two lines are separate. Okay. So if you want to connect the IC, because for IC, all the pins are independent, right? So you need to put the IC in between. Okay. But okay, we have no IC here. We have only 5 volt, which is yes, 5 volt, and the ground. And also we have three resistor, right? R1, R2, and R3. Okay. So as you can see, R1 you connect to the positive of the 5 volt, right? So R1, where is R1? This is R1. Okay. So one end of R1 should be connected to the positive side of the 5 volt, right? But since those five holes are connected together, okay. So you just need to use the jump wire to connect this point, this hole to the power box. Okay. Then that means you connect the R1 to the 5 volt. Okay. So next, let's go back to our circuit. For these three, they are connected together. It's no flat. They are connected. It's no. So this is R1. Maybe this is R2. I don't know. This is, let's say this is R2. This is R3. Okay. But at least this color, those three resistors are connected together. Right? That's what we need to put the other end, the other terminal, R1 here, and R2, R3, one terminal connected to this color. Okay. But that's it. They are not connected to the ground or connected to the power box. Nothing. But only those three terminals are connected together. But on the other side of the R2, R3, they are connected to the ground. Right? So the other side. Connected. What's wrong? Okay, I better pull this up. Yes, sir. Okay. Wrong, right? Wrong. So, the other terminals are two are three are connected to the ground. Yeah. So, the ground is go back to the power source, right? So, you have completed this circuit, simple circuit assembly in a breadboard. Yeah. But I have seen a lot of students that make this breadboard connection in a messy manner. Yeah. I'll show you the video. And other things, yeah, I see it right across again. I have played that. Okay. If you went to the vocational junior high school, vocational high school counseling, in the breadboard, I don't know what's the name of their course. I think goes through or something. Okay. They ask the student to connect all the lines in parallel all the cable around this breadboard. It's kind of messy. You know how to do the problem tracing. Yeah. So first of all, there are some rule of thumbs. First tip one is single pole wire flatly attached to the breadboard. Okay. We said the cable is flush to the breadboard. That means you need to uh, attach the cable out close to the breadboard. Okay. You cannot you cannot do the bridging. For example, some student will connect this wire and over the top of the IC and to the other point. This is very bad practice. First of all, when you want to take this out, you need to detach the cables, right? And that makes your troubleshooting more difficult. Okay, so don't over bridging. Over bridging. It's not good. Yeah, don't over bridging the component. Okay, so for example, this is not correct because this is a simple LED. But how about this is an IC? Yeah, and the IC occupies some space, right? And it's more difficult to detach those cables for replacing the IC. So don't bridging over the component. Okay, and single wire place horizontally or vertically on the breadboard. And the most important is to flush the cable on the wire. Okay, and right wire attached to the power, red wire attached to the ground. Yeah, some students use the same power. That's very bad. You need to separate the positive and the ground using different colors. Avoid directly inserting faulty component into the breadboard. For example, this is the potential meter, right? Potential meter, and those three terminals are not very thick. So when you push it, even though you can push it, yeah, but over a period of time, and the spring inside the breadboard will come loose. Okay, so it's better to use some different wire. Okay, so don't avoid directly inserting faulty component into the breadboard. And after that, after you have done, so you need to pull out all the component out. Yeah, because if you put the component inside the breadboard for a long time, and the spring will come loose. Okay, then I will show you two videos, right? And then you will know how to do a nice breadboard assembly. First one is this.
Hi, this is Dr. Ben Finio. I teach mechatronics at Cornell University, and I also design electronics and robotics projects for K-12 students. In this video, I'll be going through some of the most common mistakes I see students of all ages make when working with circuits, particularly when building circuits on a breadboard, using a multimeter, and when analyzing circuits. Let's start with the breadboard because this is something even college-age students can have trouble with if they've never used one before. As an example, we'll use this simple circuit with a battery pack, 3 LEDs wired in parallel. Hi, this is Dr. Ben Finio.
Well, the sound is connected to the sound is connected to my earphone.
I teach mechatronics at Cornell University, and I also design electronics and robotics projects for K through 12. Times we swear it's right. 9 times out of when building the circuit, if you get this flipped upside down, all the pins will be connected wrong, and your circuit won't work. Number 3, not pushing components into the breadboard all the way. This is something I've found to be more of a problem with younger students, especially if you are using these pre-cut jumper wire kits. So if we zoom in here, you'll see that all of my jumper wires are pressed pretty much flush with the breadboard, so if I pull those out, you'll see that there's actually a pretty decent length of wire that is plugged into the board. And what you'll see younger students do sometimes is just kind of just barely get the metal to make contact there, but not really push it in all the way, and then you'll have an intermittent electric contact, and you'll see that my yellow LED isn't really lighting up there until I get that in there firmly. There we go. Now the LED lights up. So again, that is especially true if you are using these tiny pre-cut wires and the students are trying to force them to a certain distance. Say if I wanted to use this yellow one to just barely bridge that gap, and you see it's a little too long to do that. So what students will do is kind of bend these inward and try to force it in like this, and then you won't get the full length of contact. They'll kind of just wind up kinking these and pressing the plastic down flat, but not necessarily actually getting the metal in all the way. So if you are using the pre-cut wires, a better way to do that, if you want a wire to be flush against the breadboard and kind of span a certain length, is actually to bend it straight first, and then bend it into a U shape, and that will give you kind of a better ability to get the metal all the way in there. And then if you want it flat, you can bend the wire sideways a little bit. So again, look out for this when working with younger students, because you're not going to have a good electrical contact there. Mistake number 4 is just having a messy breadboard in general. So it is possible to wire something correctly electrically, but just have it be sort of a mess. For example, look at the circuits on the left and right here. Electrically, these are equivalent. They're both just 3 LEDs wired in parallel. But notice how the circuit on the left is much neater. I have trimmed the leads of the resistors and cut shorter jumper wires so they're flush with the surface of the breadboard. And I've physically arranged the LEDs so they're in parallel. Whereas this one on the right here, I kind of intentionally did a bad job just using wires that are way longer than necessary. They're not color-coded. I didn't cut the resistor leads, which is always risky. When you have long parts with uninsulated leads sticking up like this, it's easy for them to bump into each other and cause short circuits. And I didn't really have a master plan to how I built this. I just kind of tossed all 3 LEDs in there. So again, electrically, this circuit is equivalent and it's working just fine, but as you start building more and more complicated circuits, this gets much more difficult to debug. So things like using short wires so you can actually trace them, color coding your wires, and again, that's something you have to watch out for with these, here it is, pre-cut jumper wire kits, is they come with nice, neat wires of different lengths, but not necessarily in the colors you want. So if you want to use red for power and black for ground, then sometimes it's better to have spools of jumper wire and a pair of wire cutters so you can cut and form your own wires of every color at the right length that you need. So again, this is something students of all ages are guilty of, including students in my college class. They'll ask a TA or somebody to come help them troubleshoot, and you see a circuit like this, and it's just kind of like, whoa, it's kind of hard for me to help you there because your wiring is so messy that it's hard to trace things or find where the errors are. So it's a good habit to do this, again, when you're building a more complicated circuit, just like if you were building something physically, to sketch it out beforehand, have a plan for where things are going to go. Don't just start throwing parts in one at a time and then, you'll run out of room or not have things line up nicely. So easy for a simple circuit like this with 3 LEDs in parallel, and more complicated when you're starting to use integrated circuits like 555 timers or op amps or something, but you want to have a master plan for how things are going to look on the breadboard at the end so it is neat and easy to debug. Mistake number 5, and this ties in closely to the previous point, not making use of the breadboard.
the most important thing is to flush the cable on the breadboard. Another thing is you need to draw your circuit first before placing the component onto the breadboard. Yeah. So you can make that first before just placing your component over the breadboard. Yeah, that's not good practice.
Power rails. So students might either not understand how to use these or just kind of forget that they exist. But on the left breadboard here, you can see I've made use of the power rails. So these are columns that are connected the whole way up and down the breadboard. So in general, the idea is that for a battery-powered circuit, I have my battery here. I have the red wire feeding into one of these and the black wire feeding into another. That gives me easy access to power and ground the whole way up and down my circuit. So in this case, my resistors just need to go right from the row with the LED over to the power bus. Then I have them both connected to the other side. I have these jumper wires just go right to the ground bus. I don't have to run long wires to connect to power and ground everywhere. If you forget to use those, like I have here, I just have my power going into one row of the breadboard, and then I kind of have to have all my resistors clustered in going to that row. Same thing on the other side, I just have my ground going into one row. I didn't use the bus, then I need multiple longer jumper wires going to that row. So especially, again, for bigger circuits with a lot of power and ground connections, that's just going to make things messy and require more or longer wires. So you always, first thing you want to do is make sure you plan to use these power and ground buses, and then that will allow you to keep your circuit neater with tighter wiring, which again is kind of a subset of the previous point. Let's move on to the multimeter. Now, this isn't really an introductory multimeter tutorial. There are plenty of other videos.
Hey, how's it going, Do-It-Yourself First? Today we're going to be going back to the basics, and I'm going to be showing you how to properly use a multimeter. And we'll be covering how to measure DC voltage, AC voltage, resistance and continuity, and also how to measure amps. Alright, let's start with DC voltage. Basically, the main source of DC voltage in the different devices that we use these days are going to be batteries. Or in other words, anything that uses batteries runs on DC voltage. For example, anything on your car that runs off the car battery, your wireless DeWalt drill, or any camera or camcorder that runs off a battery, they all run off of DC voltage. And if you're wondering, DC stands for direct current. And when you're using the multimeter to measure for DC voltage, you need to set your dial to this setting, where you get a V for voltage and the straight and dotted line for direct voltage. And next, you need to make sure your test leads are in the right location. Now, your ground or common test lead is always going to go right here where it says COM. But the red test lead is the one you're going to be switching around based on what you're measuring. And for measuring voltage, you need to place your red test lead here where you see the sign, which is V for voltage. Now, as far as where you exactly want to set this dial when you're measuring voltage, you basically want to set this to the next number up from the maximum amount of voltage you're going to be measuring. So for example, if we're going to be measuring the voltage on this 1.5 volt AA battery, we're going to set our dial to 2 volts on the DC voltage scale. Next, we put our positive test lead on the power or positive side of our circuit, and then the ground test lead on the negative or ground side. And as you can see, we got 1.6 volts, which means this is a fully charged battery. And if you're ever unsure about the amount of voltage you're measuring, you can always start off higher, like we got here on 200, and then come lower to get a more precise reading. Now, if you're ever unsure and hook up your test leads the wrong way, you're going to see this negative sign next to your voltage reading like we got here. Now, this doesn't hurt the multimeter, and it's actually a pretty decent way of finding your positive and negative side of your circuit. Next up, measuring AC voltage. And basically, any device that plugs into your wall socket uses AC voltage. And AC stands for alternating current. And when measuring for AC voltage, your black test lead stays in the same place, obviously, and your red test lead stays in the same place, since again, we're measuring voltage. But you need to switch your dial from DC voltage to the AC voltage area, and you know that by this wave sign that's next to the V here. So next, we're going to see whether we have current at a wall socket or not. And since we get about 110 volts here in the States, we're going to set our dial to 200, which is the next one up from the voltage we're expecting to measure. All right, a word of caution, when measuring high voltage like this, you need to be 100% sure of the integrity of your multimeter, plus the wires that go to your test leads and the test leads themselves. Also, when you go to take your measurement, make sure your fingers are away from the tip of the test leads, but also when you get near the socket, that your test leads don't come into contact or near each other. So next we grab our ground test lead and we're going to put this in the bigger slot on our wall socket. And then we grab our red test lead and we're going to put it on this other side, which is the power side. And as you can see, we got 118 volts coming out of this, which is about right. Also, if you ever wondered what this one is for, this is your case ground. And a good way to check it is to see whether you get a reading when you do this, and we do, so this is good as well. All right, next up, measuring resistance. And resistance is basically the amount of opposition that any substance has to the flow of electric current. So for example, this piece of wood is extremely resistant to the flow of current, whereas this wire has next to no resistance to the flow of electric current. Now, different components of an electric circuit are supposed to have a certain amount of resistance so that the whole system works properly, and that's where knowing how to exactly measure resistance is very crucial. Now, when measuring for resistance, your black test lead stays in the same place, and on this multimeter, the red test lead also stays in the same place because this horseshoe-looking thing is a sign for resistance. And we put our dial here where we get the scale for resistance. And for this example, I'm going to be measuring the resistance for this spark plug wire. And this spark plug wire is supposed to have a resistance of about 10,000 ohms. Ohms being the unit of measurement for resistance. All right, same as before, since we expect a measurement of 10,000, we're going to set our dial to the next number up, which is 20K, or in other words, 20,000 ohms. All right, here we go. And as you can see, we got 9.89 thousand ohms of resistance, or in other words, 9,860 or 870 ohms of resistance for this spark plug wire, which is about spec. All right, next, let's go on to testing for continuity. And testing for continuity basically means checking an electric circuit to see whether current can flow through it. And when testing with a multimeter, your multimeter sends a tiny amount of voltage through that circuit, and then continuity is verified, usually by an alarm or a beep. So for continuity, we set our dial here to this icon that sort of looks like a sound wave. And since we're still in the resistance setting, our test leads stay in the same area. So for example, if you wanted to make sure the wires that go to this connector are in good shape and that electricity or current can travel through them, you would attach one of your test leads to one end, and then your other test leads to the corresponding pin on the connector. And if you hear that beep, that means you got continuity. And if you do this and you don't hear a beep, it means that you got a short somewhere in this wire, or in other words, in our case, maybe a cut or a burned wire. Now, I did this test on a rather small scale, but this can be done on a much larger scale, or in other words, larger circuits, or even smaller circuits than this, like a motherboard of your computer. A word of caution though, whenever you test for resistance or continuity, you have to make sure that the device is not powered, so either unplug it or remove the batteries. Next up, how to measure amps. Now when you measure amps on this multimeter, you need to switch your test lead from this slot to one of these. Now on this multimeter, this first one is fused, which means if you measure more than 200 milliamps, you're going to blow a fuse inside your multimeter, but your multimeter as a whole is going to be saved. But this second one is unfused on this multimeter, which means if you measure more than 20 amps, you're going to ruin your multimeter. Also, if you're unsure about the amount of amps you'll be measuring, but you know if it's less than 20 amps, you can always start with this higher one and then move down for a more precise reading. So for this example, we're going to measure and see how many amps this little light bulb uses. So we put our red test lead in this setting. And next we're going to set our dial, and since this light bulb is battery powered, we're going to set it to 20 amps on the DC voltage setting. And the way you measure amps is basically you place your multimeter on the power side of the circuit you're measuring. So here's the wire from the positive side of this battery. You place your red test lead closer to the power source, and then from there power travels through your multimeter, through the black test lead, to the positive side of your device. And next, when we complete the circuit by connecting our ground side, our light bulb turns on and we get our reading, and as you can see, we got 1.95 amps. So it was a great move putting our red test lead on this higher setting to measure 20 amps, otherwise we would have blown a fuse here. And those were the basic functions of a multimeter. Hope that cleared things up. And if you found anything useful in this video, please give it a thumbs up. Also consider checking out some of my other videos where I use this multimeter to diagnose problems with my cars. I'll put on
好，给息很多。Okay, so let's talk about chapter 4. Okay, previously we focused on the filter, right? That's between the sensor and control architecture. We call it conditioning and interfacing filter. Okay, and also it occurred before the actual, not before, between the actuator and the control architecture, okay, for the output amplifier, okay. Today we will talk about the system response. That's because assume you have chosen a sensor and an actuator, and you have your conditioning interface uh, circuits ready, okay. And uh, how about this for the output filtering? Maybe not. Maybe you need to do it. Depends on how your system is response. Okay, because sometimes uh, there's no actuator in your mechanical system. Okay, but you still want to measure the response of your mechanical system. Okay, so as long as your sensor is ready and your filter circuit is ready, and of course you need to have some recording system, then you can measuring your system response. Okay, so the block diagram is like this. You need to have your input, right? And the input is coming from your sensor. Then of course it uh, recorder. Measurement system including the filter, including this two part. Okay, and after that, you can record your signal uh, using this recorder, using this measurement system. Okay, and you can record it. Okay, this chapter since we are going to measure the system response, then we need to categorize different types of your response. Is your response linear in amplitude, or is your response linear in a phase? Okay, and how wide of your bandwidth in your system? Those are the system response you are interested. Okay, and also when we look at the system response, we often look at the frequency domain, so-called spectrum. So we need to use the Fourier series to represent the signal. Okay, and also this is the measurement, and also we need to define your system. Okay, we need to model it. Okay, and because of course your system is very complicated, and it's not always a linear case. Okay, but we need to make it as simple as possible. So that's why we want to model your system as the 0 degrees of zero order, first order, or even second order of your system. And in that way, you can design design your system, right? If the system is too complicated, it's hard to design it. Okay. And next, we want to uh, measure your system output using a simple input like step function or the sinusoidal function. Okay. Then finally, we need to understand the analogy among mechanical, electrical, and hydraulic. Yeah, maybe not. We just need to understand the analogy between mechanical and electrical parts. Okay. Yep. So this is the objective of this chapter. Okay. Assume you have a sensor ready, and you have your measurement system ready, including your filter and recorder. Okay, then you can get your output. So of course you can compare your input and output. Okay, the input is uh, coming from the output of your control architecture. Okay, this is your because you output this signal through your actuator. Yeah, so you know uh, what's the what's the output of the control architecture, which is the input to your system. Okay, for example, one of my capstone project is working on the measurement of a microphone of a YouTuber, right? Because the microphone of the YouTuber is placed on the table. So sometimes if you excite the table and the microphone will measure the noise, right? So my student need to create some kind of the noise. They said they use the impact noise. For example, they drop the ball, they drop the ball onto the table. So it creates a impulse noise to the system, to the microphone of the YouTuber. Okay, so this is the input using a ball drop onto the table. Okay, and sometimes it's not. It's a controllable input by the control architecture. Okay, it depends on your case. And if you compare both signal, this is the input, this is the output. Most of the time they are different. They are different. For example, for the input of my capstone project, they drop the ball onto the table. Okay, even though it's a even though it's an impulse input, but in the frequency domain, it's a wideband input. But when you do the measurement, it depends on your mechanical system, right? So each system has their frequency response. So they are, of course, they are different from your they are different from your actual input. Okay, and also, I mean, on top of that, as I said, the measurement system includes this conditioning or interface filter, right? So it has some kind of the filtering using the filters, right? So the bandwidth most of the time is narrower. The bandwidth is smaller than your actual input. Okay. For example, in my capstone project, they use an impact. It's a wideband input, but what they are interested is only narrower frequency of their system, of their microphone. Yeah. So normally the recorder output is the bandwidth is narrower than the input. Okay. And here it says the analog signal. Okay. But nowadays, I think even though all the sensors is analog, but they have the AD converter. AD converter. Yeah. So it can transfer the analog to the digital signal. So there's no problem. So we are going to talk about the amplitude linearity, phase linearity, and the bandwidth. Okay. Okay. So what's the linearity? Of course, there's a ratio between the input and output. Okay. But that means the change of the output is proportional to the change of the input. Okay. But pay attention to this. This is the time domain signal. Okay. So for the V out at a certain of time. Okay. Say one second. Okay. Minus V out, the initial V out. This is the initial condition. Okay. So this is the voltage change from the initial condition to 1 second, for example. Okay. And the output difference will be proportional to the input difference. Okay, so this is the input, say at one second. Okay, minus the initial input. Okay, so as long as alpha is constant. Okay, then we said this system is a linear system in amplitude. Okay, because this is the amplitude. The voltage is amplitude. Not we are not talking about the phase at all. Okay, so that means the output always change by the same factor. Same factor is the constant alpha, okay, times the change in the input, times the change in the input, okay. So we called it the amplitude linearity. This is a linear system, okay. So if this is a linear system, and we, okay, there are some example here. For example, this is the time domain signal, right? This is the input, this is the output, okay. And let's pay attention to this. This is the input 0.5, right? And then for the same interval of time, the output is 10. Okay. So the factor is 10 divided by 0.5. The factor is 20. The factor is 20. Okay. So remember, the alpha should be kept the same for all the time, right? So we need to check the other time interval. For example, in this time interval, the input is 1, right? Kind of like what? So the output is 1 times 20 is 20, right? So the output should be 20. Yep, exactly. So we can call this a linear system. Okay, how about this? The input is 0.5, output is 10. Same. So the alpha for this time period is 20, right? How about the next time period? Is it a linear system? Is the ratio is 20? I asked you before. You have. How about you? Is this a linear system with the same alpha, same factor? This one. What's the alpha here? What's the factor for this period of time? 0.5, 10. Input is 0.5, output is 10. So what's the factor between input and output? 5. Alpha is output divided by input, right? I don't know if this is voltage or not, right? Doesn't matter. Output is 10, input is 0.5. So what's the factor here? 20. Yeah, 20. So is the constant keep the same for the next period of time? This is 1. How about it? What's the output here? 30, 15, 15, right? So what's the factor? Input is 1, output is 15. 15, right? So the alpha is the same or not? For the first period of time, alpha is 20. And this is, for the next period of time, become 15. So this is a linear system or not, or nonlinear system. Yeah, of course, this is nonlinear system. Good, good, good. Yeah, because I speak English, so he is a little bit hesitant. As long as you speak out, it's okay. Okay. So of course, this is not a linear system because alpha is 20 here, 20, 20. But for the next period of time, it becomes 15. Okay, because the input is 1, output is 15. So alpha is not the same. So this is nonlinear system. So uh, how about this? Of course, this is linear, but this is nonlinear, right? So of course, this is not a linear system. Okay, this is very obvious. And so, hey, where is it? too far. Okay, yeah, it jumps too far. Okay, so like I said, the ratio between the input and output is the alpha, right? So this is the output, this is the input. So we move the x in into the left hand side, and this b0 divided by a0. Those are the factors. Okay, coefficient. The ratio of the coefficient is is the alpha, right? And so we use a k here. So what's the k? K means the gain, right? The gain is the ratio between the output and input. We move the x in to the other side, right? Yeah. So k becomes the gain of sensitivity. This is very important. Okay. Normally you want to find out the gain or the sensitivity of your system. So, but pay attention of the sensitivity, since sensitivity is nothing but the output divided by input, right? Move this x in to the other to the other side. So that means the sensitivity is a relative function between the output and input. Okay. When I work in the industry, a lot of uh, a lot of colleagues don't know the sensitivity is actually the ratio between the output and input. It's a relative function. Relative function. Yeah. So if this is a linear system, no matter what's the input, okay, and the output will be changed according to this alpha, right? Right. But alpha is the same, right? So as long as you measure the relative response, x out divided by x in, and they are all the same. Okay. Please pay attention to this because a lot of my colleagues don't understand this because this is very basic in the introduction of the mechanics. OK， 就是如果这个是线性系统的话，这个 x out 除以 x in 永远是一样的，不管你的 input 是多少。OK， 好 ，so let's go back to the textbook. Okay, then we will talk about the Fourier series. Okay, this is so-called a Fourier system. A Fourier series. Fourier series is the superposition of the all the harmonics. So what's the harmonics? And that means your system, the frequency of your system response. Okay, the natural frequency of your system. So of course there are infinite natural frequency of your system because your system is actually not the first order, not the second order. They are infinite degrees of freedom, right? They are infinite. Normally, we will simplify our system as 1 degrees of freedom or 2 degrees of freedom. But in the reality, they are infinite degrees of freedom. This is the real case, right? That's why we use the finite element. Yeah, but in the reality, they are infinite degrees of freedom, right? So because of this, they are infinite degrees of freedom. So we have infinite term of in your Fourier series, okay? And because we normally want to keep it simple, so we use cosine and sine, cosine and sine. But don't forget the DC term C0 here. C0 is a DC term, and we have infinite term of the cosine and with different kind of natural with all the natural frequency. Okay, so pay attention to this. This is n omega 0 t. N omega 0 t. The n is uh, the number of your natural frequency, right? And what's the omega t? Omega t. Okay. Omega is equal to 2 pi divided by t, right? So if you move the t to the other side, then it will become radian. Okay, it will become radian. So here is the multiplication of your resonance frequency in radian. Okay, in radian, not in degree. Okay, so you have DC term and superposition of the cosine and also the superposition of the sine. Okay, for infinite number of the resonant frequency. Okay, and you can check your Fourier the theory of your Fourier series. By definition, by the theory of Fourier series, the an and the bn can be expressed like this. Can be expressed like this. Okay, but we want to find a C0, right? C0 is the DC term. Okay, so we just put a DC here. For example, for the DC term, all the ft will become C, right? And DC means there's no natural frequency, so n is equal to 0. When n is equal to 0, cosine is equal to 1, right? So it becomes a C0, integral of the C0 over the period of time from 0 to t, right? So it becomes A0. So A0 is 1 divided by t, and this is C0, right? And C0 times t, because this is the integral of C0 over the period of time from 0 to t. So it becomes 1 divided by t, C0 times t. Okay, then it becomes 2C0. So what is C0? C0 is nothing but A0 divided by 2. Yeah, very, very simple. Okay. So as long as you know the A0, then you know the C0. Okay. So what's 0 by definition is the average of your system response over one period from 0 to t, right? By definition. So you need to record the response over one period and take the average. Then you can get a C0. Okay, by definition. But 0 is nothing but A0 divided by 2. Okay. So because we want to keep it as simple as possible, right? So there are two terms, cosine and sine. Okay, and we want to combine them together. So we introduce phase angle phi n here, Okay, the phase angle is arctangent of the bn divided by an. Okay, and I think is there a drawing here? No. No. Yeah, I think we talk about this in chapter 2, right? At that time is the phi is the angle between the image. I remember at that time phi is a real part, imaginary part. Okay, using the Euler formula. Okay, so phi tangent phi is equal to for example, this is the magnitude. Okay, for example, this is the magnitude, and this is the I divided by real part. Okay, this is the phi in the complex number, phi in the complex number. But here is different. Okay, this is the phi between an and bn. Okay, but it's very similar, right? Cn is the I'm sorry. This is the imaginary part. Because Cn is actually the resultant magnitude here, right? But the 5 is actually arctangent between Bn and An. So Bn is like the imaginary part, and An is like the real part. But this is not a complex number. just a just an analogy between the complex number and the Fourier series. Okay. So this is one of the example. For example, we have some signal like this, some response like this. Okay, and this is a square response. Okay, from 0 to 1/2 of the t, 1/2 of the duration, and this is 1. Okay, from 1/2 of the duration to t, here this is -1. Okay, so we can separate the sine term. Okay, why become this is cosine, right? Or the coefficient Bn can be found from equation 4.5, 4.5, 4.5 here. So you actually want to use the sine term. Okay, you actually want to use the sine term. Okay, so so Bn can be written like this. Yeah, because there are two values from 0 to 1/2 of the duration. This is 1, right? From 1/2 of duration to t, it will become -1, right? So you need to add those terms together, okay? And you can do the integration by yourself. It will become the cosine term, okay? Cosine term. Okay, then after that, it depends on the n, okay? Because this term will become minus cosine n pi plus 1, and this term will become 1 minus cosine n pi. Okay, so it depends. The Bn will become here. Okay, because it will become 2 minus 2 cosine n pi, right? 2 minus 2 cosine n pi. So we take the 2 out. So we take the 2 out. But when the n is an even number, that means 0, 2 pi, 4 pi. Then it will become 1, right? This will become 1. So the whole term Bn will become 0. Okay. But if the n is an odd number, that means 1 pi, 3 pi, or 5 pi, it will become -1, right? So it will become 4 times 4 divided by n pi. Okay. So because all the even number are cancelled out, all the even number are gone, so only the odd number are left. So that means what the ft becomes the even number term. That means omega 0t, 3 omega 0t, 5 omega 0t. Okay, only the odd number is left. Okay, so you can write a general term like this. Those are the same. Okay. So most important thing is because we are talking about the square wave, right? Square wave. So it should be like this, okay? But if we want to, we only use omega 0, one term. Because this is sine, right? Sinusoidal term. So it looks like this. Then the sinusoidal term is very different from your square wave, right? So we add another term because this is the Fourier series, infinite number. Or infinite number of the Fourier series. So we know the first term is not correct. So we add another term. Okay. So the next one is we add the fundamental to the third harmonics. Then it becomes a little bit look like the square wave, right? A little bit look like, but not good enough. So we add another term. So we add the fundamental term, the third harmonic, the fifth harmonic, and it becomes very similar. So when you add more and more terms, the dot means more and more terms, and to the infinity of the harmonics. Okay, then finally it will become very close to the original number, original signal. Okay, so this is the beauty of the Fourier series. Yeah, but don't worry. As long as you have like a five turns, it's good enough to be close to your original signal. Okay. Yeah. normally the first DC term is very large, and the amplitude gradually decrease when we increase uh, gradually increase to the high frequency. Yeah, that's why we said when the frequency is high, it behaves more like a linear system than the low frequency. Yeah, because for the low frequency, the amplitude is very high. Normally, it becomes nonlinear. Okay, any question? No, only 10 minutes. Let's see. Okay, I will talk one more. Okay, so this is nothing but a definition of the dB. Okay, because the dB is the ratio, the ratio between output and the input. Okay, of course, in a digital world, when output is equal to input, and this is one, right? And we know this is the so-called bypass. Okay, let's just uh, take take this as example. Okay, when this is one, and the definition of the dB is 20 log 10 times 1. Okay, so the result should be 0 dB, right? Because 10 to the power of the 0 become 1, right? So if this is 1, and the result is 0 dB, yeah. So 0 dB means bypass. That means output is equal to input. Okay, but how about on the other side? If this is amplification, output is larger than the input. So that means that the term here, parentheses, become more than 1. So this is 1 point something, 1 point something. Okay, when this is 1 point something, then the dB will become larger than 0, larger than 0. So when the dB number is larger than 0, and it becomes amplification. Okay. On the other hand, if this become less than 1 point something, then the whole term will become, not the whole term, the dB value of this 20 log 10 point something, this is the -1 value, it will become negative. Okay, so it will become very clear if the dB value is 0, that means bypass. Input is equal to output. When it is more than 0, larger than 0, this is amplification. When the dB value is less than 0, this is attenuation. Yeah, and it becomes very simple. Okay, yeah, but I know for some DSP guys, they still want to see the ratio. But for system guys like me, because I'm working on acoustic, I always look at the dB. It's more clear to me. Okay, more clear to me. Okay, so 5 minutes. Okay, then normally we want to define the bandwidth, right? To define the bandwidth. How to define the starting and the end of your bandwidth? Yeah, it's hard to say, right? Here is that you need to draw a line at -3 dB, or in a linear term, it's linear scale is 0.707. You draw a horizontal line, and when you intersect your spectrum, this is spectrum because the horizontal axis is frequency. Okay, so uh, you point you mark the first intersection. This is omega L. This is low frequency. Okay, you mark the second intersection is omega H. This is high frequency. Okay, but why we define the bandwidth as a -3 dB curve? That's because when first we need to go back to our engineering, electrical engineering. Power is equal to VI, right? Power is equal to VI, and it's also equal to V squared divided by R. Okay, so we want to know the relationship between the power and our input. Okay, the input is not the input. This should be the output. Voltage should be the output, right? The power, we want to find out the relationship between the power and our output. Okay, so actually the voltage is proportional square root of the power, right? According to this, P is equal to V squared divided by R. So voltage, the output voltage is proportional to the square root of the power. Okay. So when we define the corner frequency, we call it the corner frequency or the cutoff frequency. Where is it? Corner or cutoff frequency. We pretty much specify at the area when the output is 1/2 of the input. Okay. So because of this, P A out divided by A in is equal to the square root of the power, and we define the corner frequency when the ratio between output and input is 0.5. That means 1 divided by 2, and it's close to 0.007. Okay, and when you take the dB log 10, then it becomes -3 dB. So that's why when the power is attenuated by 1/2, and the in the dB in this plot amplitude ratio, there is we just mark a straight line at 0.707 in the linear scale, or -3 dB in the dB scale. Okay, yeah. Then we know the first intersection is omega L. The second intersection is omega H, and we said where is it? Okay, the bandwidth is omega L to the omega H. You cannot subtract omega H from the omega L, or vice versa. This is not right. You just said, for example, from the 100 hertz to 10K hertz. That's it. Don't do the subtraction. Okay. 好，我很快讲一次哈，一点点而已哈。就是说，我们现在在讲的是 system response， 那回到这边哈，那 system response 呢，其实当然就是你的 mechanical system 的 response 嘛，好，可是呢，我们更多的时间是在做什么？量测，量测就是说把你的这个 system response 把它recording 下来嘛，把它记录下来，对，中文叫记录下来。所以记录下来的话，要怎么记录？最重要就是你要有这3个东西嘛，对不对？你的 sensor， 你的这个 filtering，filtering 就是说你要做一些滤波啊，然后再来是你的这个 recording 的 device， 当然你的这个 control architecture 现在很厉害嘛，它可以做 recording 哦，所以这个地方呢，就是说你的这个 input， 你的 input 是从这一边来的，是从这边来的哈。当然有时候不是从你的 control architecture 出去的，是你故意做给他的哦。比如说像我那个专题那个叫做网红的麦克风哦，他为了要模拟这个就说我们不小心敲到桌子，所以他丢一个球给他，对不对？他们说要这样做哈。那所以这个丢一个球给他，当然就不是从这边来的嘛，是他们施给外面的，施给这个桌子的一个力量 ，OK。所以这个力量就是你的这个 input， 就是你的 input， 那这个就是你的量测系统，然后你的这个 output 就是你要量测到的，对不对？就是你的 system 的这个 response， 这两个通常是不一样的哦。比如说像我那个例子呢，他丢一个球下去，那个是一个宽频讯号，因为它是一个 input 宽频讯号，所以这个是一个宽频的。可是它的这个量测出来的东西是它的 system response 嘛，哦，是那个网红的麦克风的那个 system response， 通常它比较高频，而且是一个比较窄频的东西，哦，所以这两个一定是不一样的。OK， 有这个了解之后，你就可以做后面的事情，哦，所以我们就是要了解你的 system response 的线性度，哦，当然越线性越容易控制嘛，你越容易设计啊，还有你的这个 bandwidth 是多大哦。有时候你要小一点，有时候你要大一点，不见得哦。好，所以这个 alpha 就是说你的 output 除以 input， 好，把这个移到这里来。它只要是固定的，是 constant 的话，那当然就是线性。好，这个对，好，那我们来做这个就是说你要来去 represent 你的系统的 response 的时候呢，那你通常是用一个假设是这个 sinusoid 的 input 嘛，对不对？哈、就是 sin 跟这个 cosine，对不对？我们电工学不是也这样吗？我们的这个AC 交流的这个讯号是用 sin 跟 cosine 来去代表哈。那当然你不要忘记你有这个 C0这个 term 哈。那这里每一个 term 呢都是它的 natural frequency 嘛哈。它的 natural frequency 刚刚我写在那边，我们自然界都是到无穷大，所以这边的话 n 等于1会到无穷大。但是需要这么多吗？所以这边给了一个例子，就是说，如果是这一个方波的话，那你用刚刚的这个 Fourier series 来去找它的这个 Bn， 现在它只用一边嘛，用 sin 来去逼近它。那用 sin 来去逼近它的话，它会发现说，以这个方波来讲，它剩下这个奇数的 term， 1、3、5、7这些东西。所以呢，它把这个第一个 term 跟这个方波比，好像不太像哈。然后因为它是有无穷多项嘛，一直到无穷大，所以一个项一项不一样，我们加两项好像有点近似嘛，还是不怎么像，对不对？然后再来是三项，三项就很像啊，哦，所以事实上你不用加到无穷大，你只要加5项，其实它就已经大部分就差不多，当然要看你的频率高低了哈。所以大部分的系统的话，大概加个5项就差不多了哈，就差不多了。所以我们可以用这个 Fourier series 来去代表我们这个系统的 response 这样子。OK， 好，然后刚刚最后讲到这个，要怎么定频宽嘛？因为我们刚刚前面讲线性啊，我们还没有讲 phase 哦，就讲那个amplitude 的这个 linearity。OK， 那这个频宽呢，这个是假设这个是你的这个spectrum frequency response 哈。然后我们通常来讲的话，就是在3dB 这边画一条线，3dB 这边画一条线，然后交界点呢就是你的频宽的起始点，然后还有你的这个起始跟这个上面的这个最高点这样子，用这样来去定义这个频宽。可是为什么是这样子呢？就是说我们在定义的时候，我们是以这个 power 呢降了1/2来去定义的。OK， 那根据我们这个欧姆定律嘛，这个 P 等于 VI， 然后等于 V square 除以 R， 对不对？所以这个 output 跟这个 power 刚好是output 的这个电压跟这个 power 刚好是这个 square root 的关系嘛，所以如果说 P 是用这个 corner frequency 的定义是 0.5， 把这 0.5 放进去啊，对不对？所以它就等于 0.707，所以这为什么我们要画一个 0.707 在这里？但是我们如果像我的话，我就喜欢看 dB 嘛，所以就把0.707带进去，然后就会变成3dB，所以3dB 以这个 dB scale 的话，负3dB 也是一个很简单的一个数字这样。OK， 所以有没有问题？这很重要，我常常会考这个，常常会考这个 bandwidth 到底要怎么看这样子还有就是说很重点bandwidth 常常同学算出来就比如说100到1K 来讲好了，他就把这个1K 就1000嘛他就把这1000扣100变成900，那这样我就不知道它到底900是在哪一个范围嘛？因为你这个是一个频率啊，横轴是频率这个900我知道这个900，可是它到底在这边还是在这边，对不对？一点意义也没有啊。所以你要告诉我，就是说你要写2个数字，比如说100到1000 Hz 这样子，而不是给我那个900。这很重要这个你写100到1000，我就知道它 bandwidth 是多少嘛，而且所有的 information 我就知道了。但你如果把我扣掉，我根本不知道它在哪里所以这个很重要。好，我们先上到这边。然后我会把第2章的那个封墨放上去。然后大家练习一下，然后有问题来找我，然后跟助教要一下那个教科书 ，OK。 哦，123，123，123。